Good morning to all. I am Dr.E.Purushotham, Associate Professor of Physics, Department of Physics, School of Sciences and Humanities. Today, I am going to discuss about quantum physics, or it is also called quantum mechanics. What is quantum mechanics? What is mechanics? We can explain here mechanics, the branch of study concerned with motion and force producing motion is called mechanics. So the light is divided into a small packet. That small packet is called quanta or photon. So we can go to study about quantum mechanics in our today's class. Aim of the physics and study of science. What is the aim of the physics and what is the study of the science? The aim of the science is to understand the natural phenomena around us. In the study of science, experimental and theory both are equally important in our quantum mechanics or quantum physics. The experimental results should be explained by theories. Similarly, theoretical precautions should be verified by the suitable experiments. By the end of the 19th century, there were a number of experimental results which the existing mechanics was unable to explain. Some of them are the spectrum of the black body radiation or thermal radiation, photoelectric effect, specific heat of solids at a low temperature, structure of atoms and their spectra, quantum scattering, etc. So, classical mechanics, it is also called, this is quantum physics. So, what is quantum mechanics? Already I discussed. It is the branch of physics which explain the motion of microscopic particles like electrons, protons, etc. It is introduced by Max Planck in 1900, developed by Einstein. So, what is classical mechanics? It is the branch of physics which explains the motion of microscopic objects. It is introduced by Newton in 1684. 1684. So, in order to explain the black body radiation, Max Planck in 1900 proposed the quantum theory. According to this theory, or this theory led to explain all other experimental facts successfully. The quantum theory involved in mechanics is termed as quantum mechanics. What is quantum mechanics? The quantum theory involved in mechanics is termed as quantum mechanics. The study of quantum using the quantum theory is called quantum mechanics. Quantum mechanics. So, without the quantum mechanics, the study of mechanics is known as classical mechanics. Classical mechanics. Classical mechanics successfully explained the motion of the objects which are observed or observable when the classical concepts were applied to the microscopic particles of atomic dimensions like electrons, that is microscopic. Then they failed to describe the actual behavior of the classical mechanics. So, classical mechanics and its limitations. You can see here classical mechanics, motion of microscopic objects. Classical mechanics provides extremely accurate results when studying large objects. So, what I am saying, the classical mechanics providing extremely the perfect results when studying large objectives. So, classical mechanics explains projectile motion, spring mass system, damped harmonic oscillators, etc. So, classical concepts failed to describe the actual behavior of the particle of atomic dimensions. Example, motion of an electron in an atom, projectile motion, damped harmonic oscillators, etc. So, what is quantum mechanics? Explains the behavior of matter and radiation. The quantum mechanics describes the behavior of the matter and radiation. So, it gives the close parallelism between the matter and radiation. Matter means mechanics, radiation means light. So, wave mechanics. Wave mechanics is a branch of quantum physics, deals with behavior of objects in atomic dimensions. In atomic dimensions. So, limitations or failures of classical mechanics. In our today's class, we are concentrating on these limitations of classical mechanics or why the classical mechanics cannot explain the perfect results. So, first one, stability of atom. Stability of atom. Second one, failure to explain hydrogen line spectra. Third one, failed to explain black body radiation. And failed to explain fourth one, photoelectric effect. And fifth one, Compton effect. So, stability of atom. Stability of atom. We can discuss in this first one, stability of atom. The classical model of the atom describes it as a consisting of a heavy or positively charged nucleus with lighter. You can see here simply, I'm giving the pen option here. So we can write here. We are going to discuss about classical mechanics failed to explain line spectra. So first one, stability of atom. You see here, here we know that an atom consists of heavy positively charged nucleus. This is the positively charged nucleus with light negative electrons. So the electrons, you can see here, electrons, right? So this is the positively charged nucleus. These are the electrons. The electrons are revolving around the positively charged nucleus. So we know that atom consists of a heavy positive nucleus at the center and with light negative electrons which revolves around the positively charged nucleus in circular orbits. As the electron moves, you see here, as the electron moves around the nucleus, it will experience a centripetal acceleration. We know very well about this. It is well known that an accelerated charged particle radiates energy in the form of electromagnetic waves. Therefore, try to understand here. Therefore, the energy of the electron should decrease continuously and it should come closer and closer until collapse with the nucleus. This shows that the instability of atom, this statement is, we can explain, we can observe here to the observe that fact of stability of atom. Thus, classical mechanics failed to explain the stability of this atom. So it fails to explain. The classical mechanics model of atom describes it consisting of a heavy positively charged nucleus. So what we are saying, the positively charged nucleus, for example, this is the positively charged nucleus. The electrons are revolving around the positively charged nucleus in certain orbits. As electron moves around the nucleus, the electron is moving around the nucleus. We can see here the electrons are revolving around the nucleus. So the accelerated charged particle produces electromagnetic wave. So you see here electromagnetic wave. For example, the charge at rest, it produces electric field. Electric field. The charge is moving in a conductor. It produces electric field and also magnetic field. Magnetic field. If the conductor is accelerated, conductor is accelerated, it produces a changing electric field and a changing magnetic field. This changing electric field and changing magnetic field produce a wave. That wave is called electromagnetic wave. What I am saying, at static or at rest, the electron produces electric field. If the charge is moving in a conductor, it is producing electric field and magnetic field. If the electron moving conductor is accelerated, it produces electric field and magnetic field. This electric field and magnetic field is changing due to the acceleration of the charge. The changing electric field and magnetic field produced a wave. That wave is called electromagnetic wave. That's why you clearly understand here the charge is accelerated. Accelerated charged particles produces electromagnetic wave. The energy of this electron should decrease continuously. Then the electron should come closer and closer until it is collapsed with the nucleus. It is incident with the nucleus. But we cannot observe in any atom. This shows the instability of the atom. Instability of the atom. This statement is very, very important in stability of atom. Stability of atom. So you can see here, classical mechanics failed to explain line spectra. You see here, hydrogen line spectra. Hydrogen line spectra. So classical mechanics failed to explain the line spectrum of a hydrogen atom experimentally. It is observed that the spectrum of hydrogen atom you can see here, we can see here, this is n is equal to 1, this is the Lyman series. If n is equal to 2, this is a Balmer series. N is equal to 3, Pachian. N is equal to 4, Bracket. N is equal to 5, this is the Fund strain. Fund. Lyman, Balmer, Pachian, and Bracket. Lyman, Balmer, Pachian, Bracket, and Fund series we can observe in the hydrogen spectrum. Then it consists discrete set of lines or set of energy levels, or this is the wave number. The wave number is equal to Rydberg constant into 1 by n2 square minus 1 by n1 square. So you can see here, this is nu bar. Nu bar is the wave number. Wave number is equal to 1 by wavelength. So therefore, nu bar is equal to R into 1 by n1 square, n2 square minus n1 square. Nu bar is the wave number, R is the Rydberg constant. N1 and N2 are integers such that N1 greater than N2. For example, Balmer series, we can write this is nu bar is equal to capital R into 1 by N3 square minus 1 by N2 square. So we can write for this Pachian, that is n is equal to 3, we are observing. So here, higher level, this is 1 by n4 whole square minus 1 by n3 whole square. So we can write n1, n2, this is nu bar is equal to capital R into 1 by n2 square minus 1 by n1 square. According to quantum mechanics, the excited atoms of hydrogen emit electromagnetic radiation of certain definite wavelengths continuously. In classical mechanics, there is no concept of energy quantization. Hence, it does not explain the emission of hydrogen atom. So next one, you can see black body radiation. According to classical mechanics, according to this classical mechanics, the ideal black body at thermal equilibrium will emit radiation. Emit radiation. Okay, what is black body radiation first? So, when a body is heated, it emits radiation at all the wavelengths, is called thermal radiation. The radiation emitted by the perfect black body is called black body radiation. So, what I am saying here, the black body radiation, what is black body radiation? When a body or an object is heated, it emits the radiation at all the wavelengths, is called thermal radiation. The radiation emitted by the perfect black body is called thermal radiation. That is the called black body radiation. Black body. You can observe clearly here. So, depending on classical mechanics, the ideal black body at thermal equilibrium will emit the radiation in all frequency ranges. You see here radiation in all the frequency ranges. So the frequency increases then, however, experimental results contradicts the prediction of classical mechanics. So according to Max Planck quantum theory, matter composed of large number of oscillating particles and energy of oscillating particles must be quantized. According to quantum mechanics, we have the discrete energy levels. These are the quantized. Oscillating particles does not radiate energy continuously, but it emits the radiation discontinually. In terms of discrete quanta or discrete energy levels, the prediction of quantum theory exactly match with the experimental results. So you can see here photoelectric effect. What is photoelectric effect? Already you know very well photoelectric effect. The emission of electrons from the metal plate. For example, you take here, this is a metal plate. Example, ZNS, zinc plate. The emission of electrons from the material plate when illuminated by the light or any of the radiation of the suitable wavelength. The light is incident on the plate or material with a sufficient frequency of light. From this, the electrons are emitted. So photo means light, photo is incident, electrons are produced. Electron are produced. The flow of electrons are called current. So photo is incident, we are getting some electrons, photoelectric effect. Photoelectric effect. So what I am saying here, the emission of electrons from a metal plate when illuminated by the light or any other radiation of the suitable wavelength or frequency is called photoelectric effect. The emitted electrons are called as photoelectrons and the metal is called photometal, that is photo sensitive materials. This phenomena was described by the Hedge in 1887 when he allowed ultraviolet light to fall on zinc plate or zinc blende ZNS. So we can observe here, we can observe here, photoelectric effect is the phenomena in which electrons are knocked off the metal when light of suitable wavelength is incident on it. According to classical mechanics, continuous light waves are falling on the metal. It transfers the energy to electrons, which would then be emitted when they accumulate enough, sufficient enough energy. And alternation in the intensity of light would theoretically change the kinetic energy of the emitted electrons. So the light is incident on the metal, the kinetic energy of that material has been changed. So with sufficiently dim light resulting in a delayed emission. However, the experimental results disagree with this prediction of classical mechanics. In 1905, Einstein successfully explained photoelectric effect with the help of Max Planck quantum theory. According to quantum theory, the electrons are dislodged only when the incident light photon frequency exceeds at a certain frequency, regardless of the light intensity or duration of exposure. So, the limitation of classical mechanics was successfully explained by the photoelectric effect with the help of Max Planck's quantum theory by Einstein in 1905. So, Compton effect. Okay, what is quantum effect? When a beam of X-ray radiation is scattered by a shootable of the scattered radiation, contains two components. For example, simply we can understand here the X-rays are allowed to fall on the target. The X-rays are allowed to fall on the target. So the X-ray radiation is scattered on the substance or target. The scattered radiation contains two components. This is first component, this is second component. Two components. One have the lower frequency, one have the lower frequency or greater wavelength. Lower frequency, greater wavelength because nu is equal to c by lambda, inversely proportional to. So nu is very low, lambda is very high. So here the scattered radiation, if it has the lower frequency, it has the greater wavelength. So nu is equal to c by lambda. Nu is inversely proportional to wavelength lambda. So when a beam of X-rays radiation is scattered on the substance or target, the scattered radiation contains two components, one having the lower frequency or greater wavelength, and other one have the same frequency. So it has the same frequency or same wavelength. This phenomena is called Compton effect. When X-ray beam is allowed to fall on the X-ray beam, what is X-rays? Do you know what is X-rays? So X-rays were discovered by Röntgen in 1895 after performing a series of experiments. Röntgen conducted that when a beam of fast moving electrons, you can see I am taking here, when a fast moving electrons strike, this fast moving electrons strike at a target element. So the high penetration radiation, that is electromagnetic radiation, is produced from this high energied high energied electron beam is produced. That high energied electron beam at that time, Röntgen don't know about that rays. So then he called X-rays. When a beam of fast moving electrons strike a solid target, an invisible high penetrating radiation is produced. Because of their unknown nature, Röntgen called the radiation as X-rays. So a beam of X-rays, when a beam of X-ray radiation scattered by a substance, the scattered radiation contains two components. One component has lower frequency or greater wavelength, and other one having the same frequency or same wavelength. This phenomena is called Compton effect. So the classical mechanics fails to explain this quantum effect. Why it has failed to explain the quantum effect? According to classical mechanics, scattered radiation should have same wavelength. As that of incident radiation, wavelength of scattered radiation should not show depends on the scattered angle theta. So again, you can see here. So this is one, this is two, this is lower frequency, this is the same frequency, this is the angle. So classical mechanics fails to explain Compton effect. According to classical mechanics, scattered radiation should have same wavelength for the second scattered ray as that of incident radiation. Wavelength of scattered radiation should not show depends on the scattered angle theta or scattered angle phi. You can take here, this is theta, this is the angle theta, scattered angle theta. The above prediction of classical mechanics are contrary to the experimental observations. In 1923, the Compton effect was successfully explained on the basis of quantum theory of radiation. So, depending on quantum theory of radiation, they have explained. So, classical mechanics failed to explain why. So, when a beam of X-rays is incident on the substance, the scattered radiation contains two components. The first component, why it has the lower frequency, and the second one, why it has the same frequency, they didn't explain. So the scattered angle theta, is it depending on that scattered radiation or not? The radiation should not show depending on the scattered. The above prediction, classical mechanics are failed to explain experimentally. So in 1923, the Compton was successfully explained on the quantum theory of radiation. So in order to explain the black body radiation or Planck quantum in 1900, proposed a quantum theory. He proposed a quantum theory. This theory led to explain all other experimental facts successfully. So the Compton effect also explained successfully. The quantum theory involved mechanics, thermodynamics, quantum mechanics. Already we discussed it. So without quantum theory, it is classical mechanics. Classical mechanics. So the quantum effect was successfully explained on the basis of quantum theory of radiation. You see here the main differences between classical mechanics and quantum mechanics. Simply, we can understand the limitations or failures of classical mechanics here. We can see left side classical mechanics, right side quantum mechanics. Classical and quantum mechanics. So, what is the stability of atom? What is the fail or predict to explain the classical mechanics? How it was successfully explained by the quantum mechanics. We simply try to understand here. So, number one, stability of atom, according to classical mechanics, predicts that An electron accelerating around the nucleus should radiate energy continuously, causing it to spiral inward and it will be collapsed into the nucleus. But we cannot observe that one. So, what I am saying here, this is the positively charged nucleus. The electron is revolving around the positively charged nucleus. Here, spiral inward, they are telling. So, the electrons are revolving around the positively charged nucleus. And finally, according to classical mechanics, they collapse into the nucleus. But we are not observing like that. That is the failure of classical mechanics. So, what about quantum mechanics? The quantum mechanics explain that electrons exist in discrete energy levels. These energy levels for one orbit, you see, this is the positively charged nucleus. This is one orbit, energy 1. So, energy 2 and energy 3. Simply, you can see 1. So excited state, this is E2 and so on. E1, E2 are the discrete energy levels. So these discrete energy levels do not spiral. This is the spiral mode. This is, according to classical mechanics, they explained this is the spiral inward. But according to quantum mechanics, this is the positively charged nucleus. The electrons are revolving around the positively charged nucleus. It exists discrete energy levels E1, E2. We know very well the energy from higher energy level to lower energy level, it emits H nu. So explain that the quantum mechanics explain that electrons exist in discrete energy levels. These energy levels are quantized in orbits and do not spiral into the nucleus, thus ensuring atomic stability. So, the quantum mechanics was successfully explain the stability of atoms. Next, so hydrogen line spectrum. Classical mechanics fails to explain the discrete line spectrum of the hydrogen. Lyman, Balmer, Pachin, Brockett, and Fund. So predicts a continuous spectrum without discrete lines. So the classical mechanics fails to explain the hydrogen line spectrum. But quantum mechanics is successfully explained. So hydrogen line spectrum explains about the hydrogen line spectrum. The quantum mechanics explains the discrete line spectrum of hydrogen using quantized energy levels and transition between these levels resulting in distinct spectral lines. So the quantum mechanics was successfully explained the hydrogen line spectrums by discrete energy levels or quantized energy levels. So black body radiation, you can see second one, black body radiation. So classical mechanics predicts that a black body should emit infinity energy as frequency increases, leading to the ultraviolet radiation. Radiation. So classical mechanics failed to explain the black body radiation. But quantum mechanics correctly predicts the spectrum of black body radiation using Planck's quantization of energy. Here also same due to the discrete energy levels, these discrete energy levels quantize. So according to Planck's quantum theory, the Planck's quantization of energy avoiding the ultraviolet catastrophe by describing emission in discrete quanta. So quantum mechanics successfully explained the black body radiation. So photoelectric effect. Already we discussed photoelectric effect. The sufficient light rays are allowed to fall on the metal plate or zinc blend or zinc. From the zinc plate, the electrons are released or emitted. So this is called photoelectric effect. So the classical mechanics suggests the electrons are ejected when they absorb sufficient continuous energy from light. Emission depends on light intensity and could be delayed for dim light. So why it has been happening, the classical mechanics cannot explain. So according to quantum mechanics, the quantum mechanics explain that electrons are ejected only if the incident light frequency exceeds a certain threshold. The kinetic energy ejected electrons depends on photon frequency, not light intensity. So the sufficient photon energy, the light is divided into small packets. The small packet is called quanta or photons. For example, so the sufficient light is incident on the metal plate. The electrons are emitted. Electrons are emitted. This is called effect. Photoelectric effect. If light intensity increases, the emitting electrons are not depending on that one. The intensity of light is not depending on emitting the electrons. Only the photon. One photon is incident on the plate, one electron emitted. So two protons incident, two electrons emitted. So the number of photons are incident on the plate, the number of electrons emitted from the metal or zinc blend. So you can see clearly explain that quantum mechanics explain that electrons are ejected only if the incident light frequency exceeds a certain threshold or certain frequency. That kinetic energy ejected electrons depends on photon frequency only, but not light intensity. So using this, the quantum mechanics successfully explained the photoelectric effect. So you can see the differences between quantum effect according to classical mechanics and quantum mechanics. Okay, the classical mechanics predicts that scattered radiation should have the same wavelength as the incident radiation and does not account for the wavelength shift with scattered scattering angle. Already we discussed it. So you see here, but the predicts that scattered radiation should have the same wavelength as the incident radiation and does not account for the wavelength shift with scattered angle. According to quantum mechanics, the quantum mechanics describes the Compton effect by showing that X-ray photons scattered with a change in wavelength and scattered angle aligning with observed wavelength shift. Using these words, the quantum mechanics was successfully explained the quantum effect. So next one, atomic spectra of multi-electron atoms. So according to classical mechanics, or classical mechanics fails to accurately predict the spectral lines for atoms with more than one electron due to the complexity of interactions between electrons. But quantum mechanics, we can see here, uses quantum mechanics to account for electron-electron interaction and explain the complex spectral lines observed in multi-electron atoms through advanced models like quantum field theory. So, using the quantum field theory, the atomic spectra of the multi electron atoms was successfully explained. So, you can see here tunneling effect. What is tunneling effect? So, if the particle energy is less than, for example, I'm taking here, so this is the x axis, this is the barrier, potential barrier. So, this is the energy of the particle E. This is the V naught is the potential barrier voltage or potential barrier height. If E is less than V naught, so if the particle energy E is less than the potential barrier height V naught, it is impossible to cross the barrier based on the classical idea, but it is possible based on quantum idea. So what I am saying here, if the particle is moving like this, it is not come out according to classical mechanics, but according to quantum mechanics, it is possible. According to quantum mechanics, there is a probability of transmission of a particle through a potential barrier, even though the energy of the particle is less than the potential barrier height. This phenomena is known as tunneling effect. What I am saying, if the particle energy is less than potential barrier height V naught, it is impossible to cross the barrier based on the classical idea, but it is possible using the quantum idea, tunneling effect. If the energy of the particle is less than the energy of the particle is less than potential barrier height, it is impossible to penetrate through the potential barrier. According to classical mechanics, it is impossible to penetrate or across the particle through the potential barrier. So, what is we can see here, when the particle energy is less than potential barrier height, it is impossible to across the potential barrier, but it is possible according to quantum mechanics. This effect is known as tunneling effect. According to quantum mechanics treatment, there is a probability to transmission or penetrate or can move across the potential barrier. Probability of transmission of particle through the potential barrier, even though the energy E is the energy of the particle E is less than the barrier of the height or potential barrier height. This phenomena is known as tunneling effect. Now you can observe here, according to classical mechanics, cannot explain the phenomena where particles pass through the potential barrier that they theoretically should not be able to explain based on the classical physics. But the quantum mechanics explains quantum tunneling, where particles can pass through the energy barrier due to their wave like nature, even if classically they do not have enough energy. If according to classical mechanics, they are having less energy compared to potential barrier height, then also the particle can transmit or penetrate through the barrier. This effect is called tunneling effect. The quantum mechanics was successfully explained. The quantum Mechanics of tunneling effect. Tunneling effect. Okay, next one, Heisenberg's uncertainty principle. So classical mechanics assume that position and momentum can be measured exactly and simultaneously without any fundamental limitations. So for example, position delta x, momentum delta p. We can find out this delta x and the momentum delta p simultaneously at a particular time. So you can see here in 1927, Heisenberg proposed uncertainty principle, which is a direct consequence of dual nature of matter. So according to Heisenberg's uncertainty principle, it is impossible to determine both exact position and exact momentum of the body or object at the same time. You see here what I am saying. So it is impossible to determine the position delta x and delta p momentum. Position is the delta x, momentum is the delta p. So definition, it is impossible to know the exact position and exact momentum of any object at the same time. If delta x is the position, delta p is the momentum, the uncertainty, according to uncertainty principle, it is greater than or equal to h by 4 pi. This is the Heisenberg's uncertainty principle. This is the Heisenberg's uncertainty principle. Delta x into delta p greater than or equal to h by 4 pi. H by 4 pi. Delta x into delta p is greater than or equal to h by 4 pi. So it is impossible to know exact position and exact momentum of an object at the same time. That is the Heisenberg's uncertainty principle. If we are finding delta x, we can get the uncertainty to find out the momentum. If we are calculate the delta p accurately, we cannot calculate delta x accurately. That is the Heisenberg's uncertainty principle. So classical mechanics fails to explain this Heisenberg's uncertainty principle. Classical mechanics assumes that position and momentum can be measured exactly and simultaneously without any fundamental limitations. But according to quantum mechanics, the quantum mechanics introduced the Heisenberg's uncertainty principle, which states that it is impossible to simultaneously measure both the exact position and exact momentum of particle. It is impossible to know exact position and exact momentum of an object at the same time. What we learned today? So we learned about quantum mechanics or quantum physics. What is quanta? What is mechanics? We learned. The light is divided into a small packets. That small packet is called quanta or photon. So mechanics is the study of motion and force producing motion is called mechanics. The study of mechanics using photons or quanta is called quantum mechanics, or it is also called quantum physics. Quantum physics. In 1900, Planck's quant introduced his quantum theory. According to his quantum theory, the light is divided into small packets. That small packet is called photon or quanta. The study of mechanics using photons or quanta or quantum theory is called quantum mechanics. Without using quantum theory, the study of mechanics is called classical mechanics. Classical mechanics. So you can see It is the branch of physics. Quantum mechanics is the branch of physics which explains the motion of microscopic particles like electrons, protons, etc. It is introduced by Max Planck in 1900. So this theory was developed by Einstein, classical mechanics. It is the branch of physics which explains the motion of microscopic objects. It is introduced by Newton in 1684. So classical mechanics and its limitation we can explain here. Classical mechanics, motion of microscopic objects. Classical mechanics provides extremely accurate results when studying the large objects. So, quantum mechanics explains the behavior of matter and radiation, but wave mechanics is the branch of quantum physics deals with the behavior of objects in atomic dimensions. So, you can see here the main limitations or failures of classical mechanics. So, the classical mechanics failure to explain stability of atom, failure to explain the hydrogen line spectrum, failed to explain black body radiation, photoelectric effect, explain failure to explain quantum effect, and so on. So we discussed about this stability of atoms. So we know that the electrons, this is the positively charged nucleus. Positively charged nucleus. One second. I am taking again pen option. Okay. So you see here. So according to classical mechanics, this is the positively charged nucleus. The electrons are revolving in spiral manner. Finally, the electrons are moving, revolving in spiral manner and collide or collapse in the nucleus. But according to quantum mechanics, the electrons are revolved around the positively charged nucleus in certain orbits. These are giving discrete energy levels. These are quantized. Due to using these quantized energy levels, the quantum mechanics was successfully explained the stability of atoms. Classical mechanics failed to explain line spectrum. So, according to hydrogen line spectra, so it has n is equal to 1, 2, 3, 4, 5. That is the Lyman, Balmer, Fortune, and Brockett Pond series. So using this classical mechanics, these are having different line spectra, but different series. But the classical mechanics cannot explain the discrete energy levels. But quantum mechanics explain the discrete levels. Depending on discrete levels, it was successfully explained. So black body radiation. According to classical mechanics, the ideal black body at thermal equilibrium will emit the radiation, will emit the radiation in all the frequency ranges. So according to Planck's quantum theory, matter composed of large number of oscillating particles and energy of oscillating particles. These must be quantized according to quantum mechanics. The quantum mechanics exactly match with the experimental results and it was successfully explained the black body radiation. So photoelectric effect. When the sufficient light is incident on the metal plate, from the metal plate, electrons are emitted. Effect is called photoelectric effect. So the classical mechanics fail to explain. failed to explain the photoelectric effect. So, according to quantum mechanics, it was successfully explained the sufficient frequency is incident on the metal. It emits the electrons, but it does not depend on the light intensity. So, quantum mechanics successfully explained the photoelectric effect. Compton effect. When X rays are incident on the scattered substance or object or target, the scattered radiation contains two components. One component has the lower frequency or greater wavelength, and the second one, same wavelength. And what about the scattering angle? The classical mechanics cannot explain why it has the lower wavelength and same wavelength. Why it is not depending on the scattered angle? It was not explained. Classical mechanics. So classical mechanics fails to explain quantum effect. But in 1923, the Compton effect was successfully explained on the basis of quantum theory of radiation. So this is the simple. We can easily understand the classical mechanics why it has failed, the quantum mechanics how it is successfully explained. So simply predicts that the classical mechanics predicts that an electron accelerating around the nucleus should radiate energy continuously, causing it to spiral and collapse into the nucleus. The electrons are revolving around the positively charged nucleus in spiral manner, according to classical mechanics. Due to this spiral manner, finally, the electron is incident nucleus. It is collapsed, but we cannot observe like this in any atom. So quantum mechanics successfully explained. You see, this is the positively charged nucleus. The electrons are revolving around the positively charged nucleus. So every orbit has some energy, E1, E2, and so on. E1, E2, E3, and so on. So, but it is not revolving in spiral manner. It is revolving around the positively charged nucleus in discrete energy levels. So, due to this concept, the quantum mechanics successfully explained the stability of the hydrogen line spectrum. Classical mechanics fails to explain the discrete line spectrum of hydrogen. Predicts a continuous spectrum without discrete lines. But according to quantum mechanics explain the discrete line spectrum of hydrogen using quantized energy levels, that is, the discrete energy levels, and transition between these levels resulting the distinct spectral lines. Quantum mechanics successfully explained the hydrogen line spectrum. So black body radiation, the classical mechanics predicts that a black body should emit infinity energy as frequency increases, leading to the ultraviolet catastrophe. You see, quantum mechanics correctly predicts the spectrum of black body radiation using the Planck's quantization of energy, avoiding the ultraviolet by describing energy emission in discrete quanta. So here also, due to the discrete energy levels, the quantum mechanics was successfully explained the black body radiation. Photoelectric effect. According to classical mechanics, photoelectric effect suggests that electrons are ejected when they absorb sufficient continuous energy from light. Emission depends on light intensity and could be delayed for dim light. So the classical mechanics explained the light is incident on the light intensity, but experimentally it is not correct. So the classical mechanics failed to explain this one. The light intensity is incident on the metal, the electrons are emitted. So depends on light intensity. It is not depending on the light intensity. So quantum mechanics explains successfully that electrons are ejected only if the incident sufficient frequency exceeds a certain threshold frequency. The kinetic energy of ejected electrons depends on photon frequency but not light intensity. The light is incident, sufficient frequency light is incident on the material or metal, the electrons are ejected. It is not depending on the light intensity. So quantum mechanics successfully explained. Compton effect. So classical mechanics predicts that scattered radiation should have the same wavelength as the incident radiation and does not account for wavelength shift with the scattered angle. Already we observed X-rays are incident on the target. So it gives the two rays, two radiations. So it has the lower frequency, it has the same frequency. This is the scattered angle theta. So you can see here predicts the classical mechanics predicts that scattered radiation should have the same wavelength, same frequency or wavelength lambda wavelength lambda. As the incident radiation, it does not account the wavelength shift with the scattered angle. It is not depending on the scattered angle theta. So according to quantum mechanics, it describes the Compton effect by showing that X-ray photons scattered with a change in wavelength and scattered angle aligning with observed wavelength shifts. So due to this correction, the quantum mechanics was successfully explained the quantum effect. So next one, atomic spectra of multi-electron atom. So it fails to accurately predict the spectral lines for atom with more than one electron due to the complexity of interaction between electrons. So according to quantum mechanics, uses the quantum mechanics to account for electron-electron interactions and explains the complex spectral lines observed in multi-electron atoms through advanced models like quantum field theory. So according to classical mechanics, only the line spectra are spectral lines for atoms with more than one electron. So fails to explain the more than one electron. It explains only one electron. The classical mechanics fails to accurately predict the spectral lines for atoms with more than one electron. But quantum mechanics explain electron-electron interaction and explain the complex spectral lines observed in multi-electron atoms by using quantum field theory. So tunneling effect. When the particle energy is less than potential barrier height, it is impossible to penetrate through the potential height using the according to the classical mechanics. So according to the classical mechanics, it is impossible to penetrate, to transmit the particle across the potential barrier. But it is possible using the tunneling effect. So you can see here cannot explain the phenomena where particle penetrates or pass or transmit through the potential barrier that they theoretically should not be able to classical physics. We cannot explain using the classical mechanics. But quantum mechanics explain, that is quantum tunneling, where particles can pass through energy barrier due to their wave like nature, even if classically they do not have sufficient energy. Already we discussed. For example, this is the along x-axis. So this is the potential barrier height V naught, potential barrier height. So this is the particle energy E, particle energy E. If particle energy is less than potential barrier height, so the particle cannot transmit through the potential barrier according to classical mechanics. But according to quantum mechanics, it can move, it can penetrate, it can transmit through the potential barrier. This effect is called tunneling effect. Tunneling effect. So quantum tunneling, where the particle can pass through energy barrier due to their wave like nature, even if classically they do not have enough energy. Simply, so according to classical mechanics, it is impossible to penetrate the particle through the potential barrier if the particle energy is less than potential barrier height. So according to quantum mechanics, it is possible if the particle energy is less than potential barrier height also, the particle can transmit through the potential barrier. Effect is called tunneling effect. So the tunneling effect, classical mechanics fails to explain the tunneling effect, but the quantum mechanics is successfully explained. So Heisenberg's uncertainty principle, classical mechanics assume that position and momentum can be measured exactly and simultaneously without any fundamental limitations. Only classical mechanics assumes, but it is impossible to know exact position and exact momentum. This is the position, exact position and exact momentum. It is impossible to know exact position and exact momentum simultaneously of an object at the same time. What is the Heisenberg's uncertainty principle? It is impossible to know exact position and exact momentum of an object at the same time. But in according to quantum mechanics, the Heisenberg's uncertainty principle was introduced by the Heisenberg using the Heisenberg's uncertainty principle, which states that it is impossible to simultaneously measure both the exact position and exact momentum of an particle. So these are the today's class limitations or failures of classical mechanics. So we can see simply here, classical mechanics fails to explain stability of atoms, but quantum mechanics explain successfully stability of atoms. So classical mechanics fails to explain the hydrogen line spectrum, but quantum mechanics successfully explained the hydrogen line spectrum. Classical mechanics fail to explain black body radiation, photoelectric effect. Quantum mechanics was successfully explained the black body radiation and photoelectric effect. You can see here, the classical mechanics fails to explain Compton effect and atomic spectrum of multi-electron atoms. But quantum mechanics successfully explained Compton effect and also atomic spectra of multi-electron atoms. Next one. So classical mechanics failed to explain tunneling effect and Heisenberg's uncertainty principle. So quantum mechanics successfully explained the tunneling effect, Heisenberg's uncertainty principle. So these are the limitations or failures of classical mechanics. Thank you. Thank you, one and all.